Hello, Georgi Romanic here. In today's video we are going to talk about Betz law or Betz limit, which is a theoretical concept in wind energy sector that tells us what is the maximum power that a wind turbine can extract from wind. Of course, we could phrase this question differently and say what is the maximum efficiency of a wind turbine rotor. If we have a wind turbine, in particular wind turbine rotor, and let's say it is sitting here in the middle of this frame along the line of my thigh, right here. Let's say this is upstream from the wind turbine rotor, this is downstream from the wind turbine rotor, and the wind is blowing like this. Wind speed downstream from the rotor is smaller than wind speed upstream from the rotor because the rotor extracted some kinetic energy from moving air, namely wind. What is the maximum efficiency of that extraction? Now, one might say, well, 100%. But that would be wrong, because 100% means that the wind turbine is a solid wall. Nothing is actually going through the rotor. If extraction is 100%, wind speed at the rotor would be 0. There is no more kinetic energy in the wind. And that's not good. Air would not actually pass through the rotor. You can just put solid brick wall over there. In addition, you would get pressure build up in front of the rotor, which would be actually wall, and you would have air going around because of the pressure build up, and the extraction of energy would not be very efficient. Of course, another extreme that we can cover is 0%, but that's trivial, that's easy. That means there is no wind turbine or anything to interfere with the wind. It's just wind blowing through empty atmosphere. That's zero extraction of energy, which means that the most efficient wind turbine rotor has to sit somewhere between 0 and 100%. Where on that scale 0 to 100 it sits is described by Betz law. And that is what we will derive today and discuss. Let us first discuss a sketch of this problem. We have ground, and in blue we have rotor of a wind turbine. Here we have a stream tube that is in thick black color, and we have two locations upstream of the wind turbine and another cross section that is downstream from the wind turbine. I use subscript U for the upstream velocity, and I use subscript D for the downstream velocity. Pressures are the same here, and they are P naught. Wind, of course, is coming from left to right, as you can see, and this is also my positive X direction. Swept area of this rotor is AT, area of the turbine. To find the maximum efficiency of this turbine, we have to introduce several assumptions, and they are laid out here. First assumption is that air is incompressible fluid, which means density is constant everywhere in this flow. Second, air is inviscid, which means coefficient of viscosity is 0, but more importantly, that actually means there is no drag that exists between wind and the wind turbine rotor. 3, there is no rotation in the flow. And 4, flow is one-dimensional and steady state. Steady state means there are no changes of wind speed with time. Let's first examine 6 before 5. 6 says this turbine has no hub and tower, as you can see. 5, rotor is the so-called actuator disc. What does that mean? That means rotor is made up of infinite number of blades. In reality, we usually have 3 blades, but here we assume there is infinite number of blades which actually make this rotor a disc, and that's why I call it turbine disc. And this disc is permeable, which means air can pass through the disc. It's a porous material. I would like to tell you that the most reasonable assumption here is number 1, and then they generally decay in the validity as we go down. Some of these assumptions we can account for. For example, we can introduce rotation in the flow, but then theory gets more complicated. For now, we will accept these assumptions and continue with this problem. First, I would like to address the question, why is this stream tube expanding as the wind is passing through the turbine disk? Well, the answer is turbine extracts kinetic energy from the wind, which means wind speed downstream is smaller than the wind speed upstream. Therefore, taking into account assumption number 1 of constant density, we can write equation of mass continuity as du over u plus dA over A is 0 or constant. Check my video on a continuity equation for a pipe, which means if velocity decreases, area has to increase to satisfy mass continuity. And that's what we see here. Velocity downstream decreases, therefore area of the stream tube, cross-sectional area, has to increase. Now, goal 1 in this derivation of Betz limit is to find velocity ut, which is velocity at the turbine disk. To do that, we will combine Bernoulli's equation and second Newton's law. We start with the Bernoulli's equation. Now, remember, this is a disk now, so we cannot go with a streamline through the disk. So, to account for that, we will select point just upstream of the disk, and let's call it point 1, where we will have pressure P1. And now I write Bernoulli's equation between upstream point and this point 1. And that will be P0 plus 1 over 2 rho u upstream squared, that's for this point, is equal pressure P1 here plus 1 over 2 rho u at the turbine squared. From here, we can see that pressure P1 is equal P0 plus 1 over 2 rho u upstream squared minus 1 over 2 rho u turbine squared. Now I select point just downstream from the disk, and I write Bernoulli's equation between this point where I have pressure P2 and downstream location, which means P2 plus 1 over 2 rho u turbine squared is equal P0 plus 1 over 2 rho u downstream squared, which means that P2 is equal P0 plus 1 over 2 rho u d squared minus 1 over 2 rho u t squared. I can subtract these two equations and I will get P1 minus P2 is equal, let me see, P0 will cancel, I will get 1 over 2 rho u upstream squared minus u downstream squared. And let's call this equation number 1. This is not the end of the road because I still don't know these pressures. But using second Newton's law, I will be able to eliminate these pressures as follows. We know from the second Newton's law that sum of all forces is equal mass times acceleration. And I don't need to use vectors because everything is one-dimensional. That's my assumption. So what are the forces? Well, here force is P1 times area. So that means P1 over area of the turbine disk AT minus pressure here is P2, so force is minus P2AT. Why minus? Because in this case force is acting in the opposite direction of the positive x direction, is equal mass times acceleration, but acceleration is change of velocity over some interval of time delta t. Now we know from my previous videos that m over delta T is the so-called m dot, which is mass flow rate. And I don't necessarily have to put here delta m because air is incompressible and there is no change of mass with time, which means I can rewrite this equation as P1 minus P2 times AT is equal m dot delta U. Or the right hand side is equal m dot, what is delta U? Well, that is U upstream minus U downstream. Now let's further examine what is m dot mass flow rate. Well, we know from my video on mass continuity equation in differential form that is rho A U. And in this case, that is rho A, I take A turbine, U turbine. This is generic expression, and here I am applying it to my problem. And we also know, because mass flow rate in this case has to be conserved, there is no flow entering or leaving this stream tube. This has to be satisfied at any cross section in this stream tube, which means this is equal rho A upstream, U upstream, or it is also equal rho A downstream, U downstream, or any other cross section in this stream tube. Well, with this knowledge, we can substitute that here and get that P1 minus P2 times AT is equal rho AT UT UU minus UD. Notice that AT and AT cancels, and I get that P1 minus P2 is equal rho UT UU minus UD. And let's call this equation number 2. Now notice the beauty here. I can combine equation 1 and equation 2 to get 1 over 2 rho U upstream squared minus U downstream squared, which is this, is equal to this right hand side, rho U2 UU minus UD. Of course, I cancel densities, and from here I get that UT, I want to find UT as we said, is 1 over 2 this over this, but this can be expressed as U upstream plus U downstream times U upstream minus U downstream, that's this term, divided by this U upstream minus U downstream. And notice that I can cancel these two, which means that UT is equal U upstream plus U downstream over 2. And this is very important result, and we will call it equation number 3. This tells us that the wind speed at the turbine disk is the average between wind speed upstream and downstream from the turbine disk. Now we accomplished goal 1, we found wind speed at the turbine disk, and we need to proceed to goal number 2, and that is to find power extracted by this turbine disk, and to do that we will use this result. First, let's quantify what is kinetic energy in the wind upstream and downstream from the turbine disk. I'll use another page. So kinetic energy upstream from the wind turbine is 1 over 2 mass U upstream squared. That's simple, everybody knows this formula. Similarly, kinetic energy downstream is 1 over 2 mass U downstream squared. But what is power? Because we are after power. Power, and this is now capital P, it's not pressure, it's power, is change of energy over time, and in this case it's change of this kinetic energy over time. Well, that's simple. That's this kinetic energy minus this kinetic energy. So I will get that power is equal 1 over 2 m over delta t u upstream squared minus u downstream squared. And that is equal 1 over 2 m over delta t is again m dot. I demonstrated that on the previous page, times u upstream squared minus u downstream squared, and that is further equal 1 over 2 m dot. We already saw it is rho a t u t times this u upstream squared minus u downstream squared, or power is equal 1 over 2 rho a t. Now what is ut? Well, we just showed ut is u upstream plus u downstream over 2. So we will insert that u upstream plus u downstream over 2 and times this u upstream squared minus u downstream squared. Or that is further equal, I multiply this 2 and this 2 to get 1 over 4 rho a t u upstream plus u downstream u upstream squared minus u downstream squared. Or power is equal 1 over 4 rho a t. Now I multiply these two terms. That's simple. That should be u upstream cubed minus u upstream u downstream squared plus u downstream u upstream squared and minus u downstream cubed. Or I write that power is equal 1 over 4 rho at. I will factor out u upstream cubed, and then I will get here 1 minus u downstream over u upstream squared plus u downstream over u upstream and minus u downstream over u upstream to the power of 3. And very importantly, now I introduce a substitution called A, that is ud over u, and I will even put it in red, that I will call interference factor. With this interference factor, my power equation becomes 1 over 4 rho at u upstream cubed 1 minus a squared plus a minus a cubed. And this is also a very important result because this gives us power extracted by our wind turbine based on the ratio of upstream to downstream wind speeds. Now we are still not at the end of the road because what we want to find is the efficiency of this turbine disk, and therefore we want to find ratio between extracted power, which is this, to the total power in the wind. Now, what would be the total theoretical power in the wind at the location of the wind turbine? Well, that would be power in the wind that would be here in this area AT if there is no turbine to begin with, if there is just air flowing in empty atmosphere. And that power would be 1 over 2 rho area of the turbine. So area of the turbine with the wind speed not being ut, but being undisturbed uu. So, u cubed. That is power in the undisturbed wind over cross-sectional area AT. So, when I make a ratio of these two, I will get something that is called Cp, which is power coefficient. This is capital P, so don't confuse it with pressure coefficient from wind engineering. So, power coefficient is therefore this divided by this. We can see I can cancel rho AT, and I can also cancel U upstream cubed with this to get 1 over 2, because 1/4 over 1/2 is 1 over 2, 1 minus A squared, 1 plus A. What I did, I rewrote this term as this. Sorry, it should be plus here. You can easily convince yourself that this is equal to this, because 1 times 1 is 1, 1 times A is A, then we have negative A squared, which is this, and we have negative A to power 3, which is this. And this is also extremely important result. This is power coefficient as a function of interference factor. And I can plot this functional dependency. And that's what I did right here. You can see here interference factor. Well, I can make it like this maybe, yes. You can see here interference factor A, and here on the y-axis is performance coefficient or power coefficient Cp. And you can see that this curve has the following shape. So there is a maximum in the performance coefficient for a given value of interference factor. Now, you can find this value geometrically as I did here, and you can see it's 0.3, and the Cp max is 0.59. That's one way to do it. Another way to do it that separates boys from the men and girls from the women is to differentiate this with respect to A and then set the result equal to 0. In other words, d Cp dA is equal, well, 1 over 2. I differentiate this, that would be minus 2A plus 1, that's differentiation of A, and minus 3A squared. That's when I multiply these two. And I set this equal to 0. Now again, I can solve this as a quadratic equation, but better way is to recognize that this over here can be factored in as 1 minus 3A, 1 plus A equals to 0. You can convince yourself by multiplying these to get this. We see we have two options. One option is if A is equal negative 1, but this is not physical because that means interference factor is negative, or we have other possibility that 1 minus 3A is equal to 0, and that means that A should be 1 over 3. This is the backbone of our analysis now, that tells us turbine is most efficient when the downstream wind speed is 1/3 of the upstream wind speed. One more time. Wind turbine is most efficient if the downstream wind speed is 1/3 of the upstream wind speed. Now we can finally substitute A here, and if you do that, so instead of A you substitute 1 over 3, you crunch these numbers, you will get that Cp is equal 16 over 27, which is approximately equal 59.26%. And this is the result that we were after. Let's put it in two boxes. This tells us that the most efficient turbine can extract no more than 59.26% of the energy of a fluid, in this case air. To recap what I just said is that the most efficient turbine with these assumptions is such that the downstream wind speed is 1/3 of the upstream wind speed, and this attenuation of wind speed results in the efficiency that is 59.26%. Of course, that comes with these assumptions that I laid out here. In reality, we have more losses. Well, first of all, blades are not actuator disc, but blades are finite elements. Usually we have 3 blades. Air is not inviscid, so we have actually drag exerted by turbine blades. Wind is not uniform across turbine disc. In reality, wind profile is like this. Wind speed is 0 at the surface and then increases logarithmically, quasi-logarithmically with height, depends also on the static stability. Flow is not one-dimensional and steady state. In reality, if you measure wind over time, so here is time, here is wind, you are not going to get straight line, but you will get something like this. Also, there is rotation in the flow. As the rotor is rotating, it is introducing helical flow here in the downstream section of the turbine stream tube. And also there is some air that enters and leaves this stream tube. So all these could be in principle accounted for one way or another. And more realistic value of CP is 40 to 50% rather than 59% that is theoretical maximum. This was discussion about Betz limit. Hope this video was useful for some of you that are interested in wind energy and wind turbines. Sometime later in some of the future videos we will remove some of these assumptions, in particular assumption that the flow is irrotational, and we will consider what happens if we introduce rotation in the flow. Theory becomes more complicated, but that's what we are dealing with on this channel. We are not going with some simple problems all the time. Another thing that is maybe worth mentioning is if we go back to this graph, then we can also give answer to a question: what would happen if wind turbine is indeed solid wall that I talked about at the beginning of this video, and it completely blocks the air? In other words, downstream velocity is 0. And that means interference factor is 0. And that is the here, right here. And under these conditions, the performance coefficient of the wind turbine is about 50%. So you can see that we increase for about 10%, 9.2% efficiency of the turbine if air can actually go through the rotor and not be stuck over there and a wind turbine rotor behave like a wall. Until next video, goodbye.